Hi there, I'm Boris Zalowski from Edlitera, where we strive to make learning programming fun and easy. Today, I'm going to tackle a very important topic, and that's the concept of machine learning ensembles. Now, you might be wondering, why should we focus an entire video on machine learning ensembles, right? Well, let me explain. You see, ensembles function like a stepping stone from basic models such as support vector machines, linear regression models, logistic regression models, and other similar models towards the territory of more advanced algorithms. In other words, if you leap straight from simple models to very advanced models, such as boosting algorithms and even deep learning algorithms, you'll be missing some foundational knowledge necessary to completely understand how these advanced models work. Therefore, in this video, I will teach you what ensembles are, and I'll also demonstrate how you can create an ensemble by combining multiple machine learning models together. As always, if you find this video helpful, please leave a like and hit the subscribe button. It helps us very much in growing our channel, and it also makes sure that we can keep providing you with more high-quality educational content. And now, without further ado, let's get started. So what exactly is ensemble learning and how does it work? Well, the idea behind ensemble learning is actually quite simple. Instead of training a single model and relying on its prediction, we're going to train multiple models and we're going to combine their predictions together. This should, in theory, give us a better overall accuracy. Now, why does this happen? Well, very often when we train a single model, that model ends up being a weak learner or a model that barely outperforms random guessing. This means that its performance is so bad that it can't be actually used in production. However, using ensembles, we can combine multiple of these weak learners together to get a so-called strong learner, a model that significantly outperforms random guessing. Why does this happen? Well, when we use multiple models, each one of these models sees data a little bit differently and makes different mistakes. Some models might be good at understanding one part of our data. Other models might be better at understanding another part of our data. So when we put all of these models together, their strengths can cover for each other's weaknesses. This will give us a better overall result. This is kind of like asking a group of people a question instead of asking just one person a question. If you ask a group of people, you will typically get a more balanced answer. Let's look at it from the perspective of machine learning. Let's say that we have a task where you need to classify a document into either class A or class B. Instead of training a single model and letting that model decide whether the document should be a member of class A or class B, we can train, for example, 5 models. If 4 out of those 5 models say that the document should belong to class A, and only one model says that the document should belong to class B, we can safely predict that the document should actually belong to class A. Now, this is just one example of ensemble learning. To be more precise, this is what we call voting. We also have other techniques such as bagging, and this is what we're going to focus on in this video. Voting is the first ensemble method we need to talk about. It's a very popular ensemble learning method, typically used in the context of classification. There are 2 types of voting, hard voting and soft voting. In hard voting, each individual model in the ensemble votes for one class, and the class that gets the majority of the votes is predicted as the output. For example, take a look at the image that's on the screen. We have 3 classifiers. 2 classifiers are voting for class A, and 1 classifier is voting for class B. Because we have 2 votes for class A and just 1 vote for class B, using hard voting, our ensemble is going to predict that the correct output should be class A. In soft voting, on the other hand, every classifier will provide us with a probability value for each class. In this case, we have 2 classes, class A and class B. So from each of our classifiers, we are going to get 2 probability values, one for class A and one for class B. The way we calculate the final probability value is by summing up the individual probability values and dividing them by the number of classifiers. So for example, if we want to calculate the final probability value for class A, what I'm going to do is I'm going to sum up the probability value I got from the first classifier, which is 0.11, with the probability value I got from the second classifier, which is 0.51, with the probability value I got from the third classifier, which is 0.55. The sum of these 3 values is 1.17, and when we divide it by the number of classifiers, which is 3, we get 0.39. This is how we get this final probability for class A, and to get the final probability for class B, we follow the same principle. In the end, to use soft voting to predict our final output, we're just going to compare the 2 final probabilities. In this case, because the final probability for class B is bigger than the final probability for class A, we are going to predict class B. Bagging is the type of ensemble learning where we take several copies of the same model and we train those copies on different samples of our original data. The way we get those different samples is by performing bootstrapping or random sampling with replacement. Performing random sampling with replacement means that you pick items from a group one at a time, and after each time you pick an item, you put that item back in the group before picking again. This means that every item always has an equal chance of being picked, and it also means that sometimes we will run into duplicates in our samples. Once we create these training datasets using bootstrapping, we can go ahead and train each one of our models on each one of these samples. So we will train the first model on the first sample, the second model on the second sample, the third model on the third sample, and so on and so forth. Finally, we aggregate the predictions, basically combine them together to get to the final prediction of our ensemble. Typical example of one such model is the random forest model. In a random forest model, we take our original data, we perform bagging to get multiple datasets we can use for training, and then we train a decision tree model on each one of those sample datasets. In the end, we combine the predictions of these decision tree models together and get the final prediction of our random forest model. To demonstrate how we create ensembles, I'm going to create a voting ensemble. We talked about bagging ensembles, however, those are more complex, and models such as the random forest model merit a video of their own. So in this particular example, I'm going to use pandas to load in my data and create a data frame. Then I will use the train test split function to split my data into a training set and a testing set. I will prepare my data, or to be more precise, I'm going to scale it using the standard scaler from scikit-learn. Then I'm going to create a voting ensemble, which will consist of a logistic regression model, a decision tree model, and a support vector machine model. I will train that ensemble, and finally, I will evaluate the performance of that ensemble by creating a classification report. Here at the beginning, I'm importing everything I plan on using in this particular example. Now I can go ahead and load my data into a data frame. To do so, I'm going to use the read CSV function from pandas. It's very useful because I can load my data directly from an S3 bucket. In this case, it's our S3 bucket where the data set currently is stored. Now, the data that we'll be working with in this example is the iris dataset. It's a very famous dataset. Essentially, it consists of 5 columns. The variety column is essentially our label column. It consists of 3 unique values, as you're going to see in a few moments. We have 0, 1, and 2. These represent 3 different types of iris flowers. And the way we're supposed to essentially predict what type of flower it is by using the sepal length, sepal width, petal length, and petal width features. So what am I going to do? Well, I'm going to separate my independent features from the dependent feature. So essentially, I'm going to put all of the features except for variety, my label, into X, and I'm going to keep my label into Y. Then I'm going to split my data set into a training set and a test set. To do so, I'm going to use the train test split function from scikit-learn. I just need to specify what I want to split. In this case, my independent features and my dependent feature. I need to specify how big I want my test set to be. In this case, I'm defining that I want it to be 20% of my overall data. And finally, I'm just using a random state here. I'm defining a seed to make sure that my results are repeatable. Now, after I split my data set into a training set and a test set, I need to pre-process my data. In this case, the whole data set is clean. The only thing we need to do is scale our data. To scale the data, I'm going to use the standard scaler from scikit-learn. First, I'm going to define the scaler and store it inside of the scaler variable, and then I'm going to scale my features. Remember, we always fit the scaler only on our training data, never on the test data. So what I'm going to do is I'm going to fit transform my training data, but I'm going to just transform my test data. And at this point, my data is completely ready. Now I can create my ensemble. How am I going to create the ensemble? Well, first I need to define the 3 models that my ensemble is going to consist of. And this is going to be my logistic regression model, decision tree model, and support vector machine model. I'm going to store them inside of the variables first classifier, second classifier, and third classifier. And after I do so, I can create my ensemble. The way we create our ensemble is by using the voting classifier from scikit-learn. Now, 2 things that I need to input here. First, what type of voting do I want to use? In this case, I decided to use hard voting. And also I need to define what my estimators are. Now, this parameter right here actually defines what models we're planning on using. So what we need to input is a list of tuples. Each tuple consists of the model we plan on using and how do we want to name that model. In my case, I decided to just use the names of the models themselves. So this could be, for example, first model, second model, third model. It doesn't need to be the exact name of the model. The only thing that's important is that the second member of each of these tuples is the model that we've defined and stored inside of a variable. So at this point, after I define this ensemble, I can go ahead and train the model. We train ensembles the same way we train any other model in scikit-learn. So I just use the fit method on my training data. And because our training data consists of only a very small number of examples, to be more precise, we have 50 examples of class 0, 50 examples of class 1, and 50 examples of class 2. 20% of that goes to the test set. So essentially 80% of this 150 is used for training. So that's why the training is finished so quickly. Finally, after I have a trained model, I can use the predict method of my Ensemble on my test data to make predictions. Now that I've made some predictions, I can go ahead and use the classification report function from scikit-learn. I just need to input my test labels. I need to input my predictions, and it's going to return a classification report. If I print that report, the end result is going to look like this. So as you can see here, we can see the precision, recall, and the F1 score for each one of our classes. So it seems that our model is basically perfect at predicting class 0. So it's always correct. When it comes to class 1, it's not as good, and especially when it comes to class 2. But overall, the F1 score of our model, the weighted average F1 score of our model, which is very important if you're working on a multi-class problem, such as this one, is 0.97, which means that our model, our Ensemble method, overall performs pretty well. It makes pretty good predictions, especially considering the fact that we are working with only 150 examples in total in our training dataset and test dataset combined. In this video, I explained what ensembles are, why do we use them, and I also demonstrate how you can create an ensemble of machine learning models. That's everything you need to know about machine learning ensembles, and at this point, you should be ready to start using them in your own projects. If you found this video helpful, please consider giving it a like and subscribing to our channel as a way of showing your support. By doing so, you contribute to the growth of our channel, which further encourages us to continue producing high-quality educational content for you. Thank you for watching, and see you next time.